Hi Geometry, let's review some exponent rules that we're gonna be using. So first of all, we have the product rule. This is when we have like bases, and the shortcut is we get to add the exponents. So let's look at an example of this. If I have x to the third times x to the fourth, let's think about what that is. That is x times itself 3 times, that's my x cubed, times x times itself 4 times, 1, 2, 3, 4. That is x times itself 7 times. That's why the shortcut for when we are multiplying like bases is to add the exponents. So let's look at an example of this here. I have 2 to the fourth times 2 squared. The 2 is my like base. Notice that I don't make it a 4, I keep it a 2. That's my like base, and I add my exponents. 4 plus 2 is the 6 that you see there. Let's take a look at A. My like base is x. Notice that I just write an x. And now I add my exponents, in this case 3 plus 8, and that's where I get the 11. So let's take a look at C. C, I'm going to reorder these right here. This is an x squared. I'm going to put the x cubed next to it. Then I'm going to write the y to the first. And then I'm going to write the y to the fourth. And we can see that we have a like base of x to the 2 plus 3 power, or 5. And my like base of y to the 1 plus 4 power, or also 5. What about our quotient rule? This is when we have like bases, and this time we subtract the exponents. So let's look at an example of this. I have x to the 7th divided by x squared. Let's think about what that really means. It means x times itself 7 times. 4, 5, 6, 7. Divided by x times itself twice. So we're going to get to cancel from the numerator denominator one pair of x's. We're going to get to cancel a second pair of x's. And what do you know? I have x to the 5th left over. X times itself 5 times. So if you notice here, I have a like base of x and x. That's my base. And then 5 minus 2 would give me my exponent of 3. I have a like base of 3. Notice my base of 3. It doesn't change to a 1 or anything. And I do 5 minus 3 and I get my 2. Same thing here. 2 minus 1 is 1. And 5 minus 3 is 2. So now the 0 exponent rule, anything to the 0 power is equal to 1. You can take a look at those examples. The power rule we've talked about in class. This is an exponent to another exponent. We get to multiply those exponents. So let's look at A. If I have x cubed times itself twice, that's what x cubed squared means. This now becomes a like base problem where I'm going to add my bases and get x to the 6th. So this is why my shortcut to multiply my exponents work. I really have x times itself 6 times. That's going to make it x to the 6th. So when you have bases inside of a parenthesis, you can allow that exponent to go to each base. So for example, let's take a look at A. They have 2a to the 3rd power. Notice that they now rewrite it as 2 cubed times a cubed. 2 cubed is 8, so I get 8a cubed. You can look at the other examples on your own time. So the next one's really quite important for what we're going to be doing. Negative exponents. The sign of the exponent changes the location of my base. So for example, if I have x to the negative 2, that means that I'm going to do the reciprocal of this. I'm going to move my x from being in the numerator, if I could put it over 1, to being in the denominator to a positive 2. That's what the negative's really doing. It's flipping where my base is. So let's take a look at A. A is very similar to what I've just done. It was an x to the negative 3. So to clear that out, I rewrote that as 1 over x cubed. Take a look at B. it was 4 to the negative 2. So in order to make that exponent not negative, I rotated my 4 to the denominator to a positive 2. It's 1 over 16. So let's take a look at D for just a moment. This has a numerator and a denominator to the negative 3. So you can think about this one two different ways, but notice the way they show it. They go ahead and do the reciprocal. They flip the y to the top and the x squared to the bottom, and then they put it to a positive 3. So they flipped it. Their denominator came to the numerator came to the denominator, and now it's to a positive 3. And then notice they use the expanded power rule above, and they let it be y cubed over x squared to the third power, and I multiply when I have an exponent to an exponent. So if you have 7 to the negative 2, this means that I really have 1 over 7 to the positive 2, and that's going to give me 1 over 49. So let's take a look at the next page of our packet. This is a completely optional page, but you'll notice that the problems up above all have answers below. If something up here was really confusing to you, you want extra support or to understand what's happening, please don't hesitate to come ask me, but this page is not assigned. So let's take a look at what is assigned. Let's go through and do a few of these problems. So let's take a look at the directions. It says to determine the missing exponent that would go in the box to make the equation true. So we're going to have to use negative, possibly rational or fractional exponents, and then it does say that some of them might have no solution. So let's take a look at 3, 4, 7, and 8 together. So I have a base of 3, and I would like to get an 81, so my number gets bigger. So I think about 3 times itself, how many times would be 81? And so I think about 3 times 3 is 9, times 3 is 27, times 3 is 81. It looks like my missing exponent would be a 4. So now let's look at number 4 carefully. My base is a 4, but notice that my answer is in the denominator. So I probably have a negative exponent. This is what my mind is thinking about. And since it gets bigger, it was a base of 4 and it becomes a 16. I think about the fact that 4 squared is 16. So I consider that 4 to the negative 2 would be 1 over 4 squared, or 1 over 16. It looks like my missing exponent would be a negative 2. Anytime my base goes to my denominator, I want to consider maybe a negative exponent. Let's take a look at number 7. So my answer goes negative. Very often, what students automatically think is 4 to the negative 1. They just see that 4 stays a 4, it doesn't change, it must be 4 to the first power, but it becomes negative. But let's think about what 4 to the negative 1 is. 4 to the negative 1 would mean 1 over 4 to the positive 1. It's really 1/4. It's not negative 4. So let me erase that thinking, because we don't want to think that way. Number 7, there's no exponent you can raise something to and change the sign. So this particular one is an example of a no solution problem. There isn't an exponent that exists that will create a negative number when your base was positive. So now let's take a look at number 8. Anytime your answer is getting smaller, you should probably consider a rational exponent. So I'd like the 27 to become a 3. In other words, I'm going to think for a moment, is there any root I could do on 27 to get this smaller number of 3? And there is. I could do a cubed root on 27. So a cubed root written as a fraction would be 1/3. Remember, your root is in the denominator. So it looks like I'm missing a 1/3 in this problem. So before we go, let's take a look at number 20. don't really want to give 20 away, but every year a lot of people ask about 20. So let me write a different problem here. Let's do negative 1 over 27 to some exponent, and I'd like to get a negative 3. Huh. Okay, well, I like that they're both negative because I know there's no exponent that will change the sign of my problem. But I do notice my base, my 1 over 27, my 27's in the denominator, and my 3 is in the numerator. So right away I'm thinking about maybe a negative exponent because I'd like the 27 to go up into the numerator. But the 27 also gets smaller. It was 27 and now I want it to be a 3. So maybe a rational exponent, because I want the bigger number to become smaller. And a couple things I'm thinking about. I know the cubed root of 27 is 3. And I also know the cubed root of negative 27 is a negative 3. This seems somewhat important to this problem. And I also know that if I have negative 1 over 27 and I raise that to the negative 1 power, I'm going to now have negative 27 up in the numerator. So I think not only do I have to have a negative exponent here, a negative exponent, but I also have to take the cubed root of this. I think it might be negative 1/3. Let's practice this down below, shall we? Negative 1 over 27 to the negative 1/3. So many things going on. Why don't I take care of the negative exponent first? So I'm going to rewrite this as negative 27 to the 1/3 power. Notice I got rid of this negative because I went ahead and did the reciprocal. I rotated my denominator up to the numerator. Notice I didn't change my sign. My problem was negative before. My problem is negative now. So now I'm going to take the cubed root of 27, and that's going to give me a negative 3. That's the answer I wanted. So it does look like, and let me change the color of my pen so it sticks out. It does look like this was a rational exponent, and it was a negative rational exponent. That's some thoughts that might help you on number 20. Thank you very much.